Sci-fi loves teleportation. It's a surefire way to fill in plot holes and create all kinds of fan angst. But how awesome would it be to actually teleport? Want to find out how? This is the Science of Sci-Fi. Last time in Dystopia, our time-crunched hero or undefeatable villain disintegrated at Portal A/Beam A/Booth A, and they rematerialized at B. You might not actually be moving from one place to another, but you do have to get enough information and materials from A to B to reconstruct the object. Think of teleporting as long-distance 3D printing, except the original box is destroyed. Not that complicated, right? Well, because we can't just have ink and plastic at the other site. In order to teleport this apple, we have to find out where every single atom is right now to recreate it. And here you run into a problem. Namely, the uncertainty principle of quantum mechanics. Essentially, we can't know both where an object or particle is and how fast it's moving at the same time. Except scientists are the ultimate loophole finders. Introducing quantum teleportation. You've heard of quantum physics before, right? That thing people make nerd jokes about because nobody actually has any clue what it is. One property of quantum mechanics, entanglement, is the key to working around this we need the info problem. And it may just lead to hyperspeed computers and possibly the future of technology. So listen up. What is quantum physics? The universe runs in two ways. Classical physics, we're talking Newton's law, throw a ball up, it'll come back down physics, and then you have quantum physics. Quantum physics is how particles work at the smallest possible scales. A key part of quantum physics is the ability for a particle to exist at multiple places at once. If you've ever heard of Schrodinger's cat, a cat is put into a box with a bomb that has a 50% chance of blowing up and killing the cat. If the cat were a quantum object, like a photon, it would be both alive and dead at the same time. Take a second to think about that. The object isn't here or there, it's 50% here and 50% there. This phenomena really couldn't happen in classical physics. If you have a cat in a bomb box, it's definitely alive or dead. But quantum particles operate differently. This is the classroom view of an atom. Reality is more like this, a cloud of electrons, with one particle existing everywhere at once. But you won't ever see the electron everywhere at once because state's set when we observe them. That quantum cat may be both alive and dead in the box, but once we look inside, the state is broken and it's back to plain dead or alive. As soon as we measure where the electron is, it's either there or it's not. Quantum physics isn't the question of where the electron is right now, it's more a probability. When we measure, we have a 30% chance of finding the particle here versus a 5% chance of finding it here. And now we turn to entanglement. Instead of a cat, we have two particles, A and B. The two states, life and death, are replaced with states we call spin. And there's a certain chance, we'll say 50-50, of A having spin up or down. Same goes for object B. So if you put them together, we have a 25% chance of A being up and B being down, 25% chance of A being down and B being up, and so on. But entanglement lets us narrow this down a bit. Entangled particles are linked so that if A has spin down, B must have spin up. If A has spin up, B has to be down. One is always the opposite of the other. If cat A is alive, cat B must be dead, no matter how far apart they are, no matter if there's no way for them to contact each other. How do they communicate even if they have to go faster than light speed? We don't know. But this instant communication is the key to super fast computing, and it's one of the practical applications of quantum physics. We're going to teleport a photon, a light particle, represented for drawing's sake by an apple. Again, the uncertainty principle says that we can't know everything about the apple, not enough to teleport, but this is where the entangled stuff comes in, because we do know the properties of A and B. So we send one of the entangled particles, A, at the apple, and they mutually destroy each other. But if we measure the collision, we can get enough information to reconstruct with only partial knowledge of the apple. At the receiving end, we take the information we got from the collision and rebuild what I'm calling the rough sketch of the new object. But to make it into a real teleport, we need the rest of the information to put every particle in the right place. So we take the other entangled particle, B, and use a treatment to reconstruct the rest of the apple. If B has spin down now, we know that A had spin up going in, and we can use this information to reconstruct the rest of the apple based on the collision data. And voila! New teleported apple. So big question. Will humans ever be able to use quantum teleportation as transportation? Probably not. As of late 2014, we've managed to teleport a photon 25 kilometers. That's impressive. But that's also a light particle. It literally has no mass. To quantum teleport, you have to find some way to get the information from station A to station B. Transporting, let alone collecting all that information from a human being, would take more years than the universe has existed. So, sorry, you're not going to be able to beam back home and grab your forgotten homework. But the same science may lead us to quantum cryptography, super speed computers, and a new age of technology. So at least you'll have faster Wi-Fi.